There is something strange about the fact that you exist. The universe, by almost every calculation, should have erased itself before it ever truly began. Welcome to the Sleepy Lab. Tonight, we drift through one of the quietest and most profound mysteries in all of physics. Why the universe contains something rather than nothing. Why matter survived. And what that survival cost. If you find this kind of wondering restful, consider subscribing. We explore the science of sleep and the universe that holds you while you rest, one sleepy soul at a time. Now, let's begin. The universe contains roughly 10 times more matter than antimatter. That sentence sounds simple enough, but sit with it for a moment, the way you might sit with a sound you cannot quite place in the dark. Because that small imbalance, that quiet tipping of the scales, is the reason stars exist, the reason planets formed, the reason there is a body lying in a bed tonight, breathing slowly, drifting towards sleep. And no one fully understands why. To understand the mystery, we have to go back, very far back, to a moment roughly 13.8 billion years ago, when everything that exists, all the matter, all the energy, all the space itself, emerged from a state so dense and so hot that our ordinary language barely reaches it. In the first moments after the Big Bang, the universe was not filled with atoms or stars or anything we would recognize. It was filled with pure energy. And that energy, as it expanded and cooled, began to do something remarkable. It converted itself into matter. But not matter alone. For every particle of matter that formed, a corresponding particle of antimatter formed alongside it, a mirror twin, identical in mass, opposite in almost every other way. This is not a theory or an assumption. It is a consequence written into the deepest equations of physics. Energy, when it condenses into a particle, produces two. Always two. One of matter, one of antimatter, born together in the same instant. For a brief and extraordinary time, the early universe held both. A vast, seething plasma of particles and their twins, colliding and separating and colliding again in the unimaginable heat. And then, as the universe expanded and cooled, something inevitable began to happen. When a particle of matter met its antimatter counterpart, they did not simply pass through each other. They annihilated. Both particles, matter and antimatter alike, were completely converted back into energy. Gone. Not destroyed in the way a candle flame goes out, leaving wax and air behind. Gone entirely, transformed, returned to the light from which they came. This process is called annihilation, and it is total. A proton meets an antiproton, and both become gamma rays, the most energetic form of light that exists. An electron meets a positron, and both vanish into a brief, brilliant flash. No remnant, no residue, only light. Now hold that image quietly for a moment. A universe full of matter and antimatter, meeting and erasing each other in equal measure. If the balance had been perfect, if matter and antimatter had been created in exactly equal amounts, this process would have continued until nothing remained. No protons, no electrons, no atoms, no moleculas. Only a vast, cooling sea of light, spreading outward through an empty universe. No galaxies would have condensed from that light. No stars would have ignited. No planets would have formed from the slow gathering of dust and gas. No oceans, no continents, no living cells dividing quietly in the dark. Nothing. Just light, traveling forever through a universe with no one in it to observe it. And yet, here you are. Something went slightly, almost imperceptibly wrong with that perfect cancellation. Or perhaps, depending on how you hold the thought, something went slightly right. For every billion matter-antimatter pairs that formed and annihilated in the early universe, there was one extra particle of matter. Just one. Not two, not 10. One among a billion pairs. A difference so small, it is almost impossible to feel the weight of it. One part in a billion. And yet that difference, that single surviving particle for every billion that vanished, was enough. When the Great Annihilation was over, when matter and antimatter had found each other and erased each other across the entire young universe, that tiny remainder was left behind. Uncancelled. Alone in the cooling dark. And from that remainder, from those 1 in a billion survivors, everything was built. Every star, now burning in the night sky, traces back to that excess. Every planet, every ocean, every grain of sand on every shore. The carbon in every living cell. The iron at the center of every star. All of it descended from particles that simply had no antimatter twin to meet. Physicists have a name for this imbalance. They call it the baryon asymmetry of the universe. A baryon is a particle made of 3 quarks. Protons and neutrons are the most familiar. And the asymmetry between baryons and their antimatter counterparts is measured at roughly 1 part in a billion. A number that is, in one sense, almost nothing. And in another sense, everything. The question that has occupied physicists for decades is a quiet but urgent one. Why was the balance not perfect? The laws of physics, as we understand them, suggest it should have been. Matter and antimatter should have been produced in equal amounts. They should have found each other completely. They should have left nothing behind. And yet the universe we observe, the one that contains you, and the bed you are lying in, and the slow rhythm of your breathing, tells us that something in those early moments broke the symmetry. Something treated matter and antimatter differently. Something tipped the scales by 1 part in a billion, and then, apparently, stopped. This breaking of symmetry has a name in physics. It is called CP violation, the idea that the laws of nature do not look exactly the same when you swap particles for antiparticles and reverse the mirror image of space. CP violation has been observed in experiments. In the decay of certain unstable particles, matter and antimatter behave in subtly different ways. The difference is real, confirmed, measured with great care. But here is where the mystery deepens, and deepens quietly. The amount of CP violation that the standard model of particle physics predicts, the best and most complete theory of matter we have, falls far short of explaining the asymmetry we observe. Not slightly short. Short by many orders of magnitude. The theory accounts for a difference, but not nearly enough of one. Something else must have tipped those scales. Something not yet written into our equations. Something the universe knows and has not yet told us. And so the question remains open. Patient, unhurried, waiting in the dark the way all deep questions wait. Why does matter exist? Why did 1 particle in a billion survive when all the others canceled out? Why is there something, this breath, this body, this quiet night, rather than nothing at all? No one knows. Not yet. Physicists have a name for this imbalance. They call it the baryon asymmetry of the universe. It is a quiet, technical phrase for something almost impossibly profound. A baryon is a particle built from 3 quarks bound tightly together. Protons are baryons. Neutrons are baryons. And so the matter that makes up every atom of every star, every grain of dust, every living cell, all of it is baryonic matter. All of it is made of these small, dense, 3 quark structures that somehow survived when their antimatter counterparts did not. The asymmetry between them is measured as roughly 1 part in a billion. 1 in a billion. If you lined up a billion matter-antimatter pairs and let them annihilate, let them cancel each other completely, pair by pair, until the light faded and the energy dispersed, one particle would remain. Just one, sitting quietly in the silence where a billion others had been. That is the margin by which the universe exists. Not a large margin, not a comfortable one. A margin so thin it is almost not there at all, and yet it was enough. Enough for galaxies to form, enough for stars to ignite and burn for billions of years, enough for planets to cool and settle into orbits, enough for the slow, patient chemistry of life to begin. All of this from one part in a billion. It is worth sitting with that for a moment, not with urgency, just with a kind of quiet wonder. The universe did not need much of an advantage. It only needed the smallest possible one. And it had it. For a long time, no one had a framework for thinking about how such an asymmetry could arise. The laws of physics, as they were understood, seemed to point toward perfect balance. Matter and antimatter created equally, annihilating equally, leaving nothing behind. And then, in 1967, a Soviet physicist named Andrei Sakharov wrote something down. Sakharov was already known for his work on nuclear weapons, a man who had spent years at the center of enormous destructive power and had grown, over time, into one of the most important voices for peace and human rights in the 20th century. But in 1967, he turned his attention to a different kind of question, a quieter one. Why does matter exist at all? He identified three conditions, three things that would have to be true. Three things that would have to have been true in the very early universe for matter to come to dominate over antimatter. These conditions are now called the Sakharov conditions, and they remain, more than half a century later, the foundation of how physicists think about this problem. The first condition is this. There must have been processes in the early universe capable of changing the number of baryons. This may sound simple, but it is not. In the physics we observe today, baryons are conserved. A proton does not simply appear from nothing, and it does not simply vanish. The total number of baryons in any interaction stays the same. If you start with 2 baryons, you end with 2 baryons. The count is preserved. But Sakharov recognized that if the universe began with equal amounts of matter and antimatter, if the baryon count started at 0, perfectly balanced, then something must have been able to disturb that balance. Some process must have been able to create baryons without creating an equal number of antibaryons, or destroy antibaryons without destroying an equal number of baryons. The count had to be changeable. Otherwise, the asymmetry could never have arisen at all. You cannot get to 1 in a billion from 0 if the rules forbid the number from ever shifting. So the first condition asks for a crack in the conservation law, a door, however small, through which the balance could tip. The second condition goes further. It requires that the laws of physics themselves treat matter and antimatter differently. This is the condition that connects to CP violation, to everything that was discovered in those careful experiments with kaons and B mesons, the subtle, measured difference in how matter and antimatter decay. If the laws of physics were perfectly symmetric, if every process that could happen to a particle could happen in exactly the same way to its antiparticle, then even with baryon number violating processes, the universe would still end up balanced. Any process that created an extra baryon would be perfectly mirrored by a process that created an extra antibaryon. The asymmetry would wash out. For the imbalance to survive, the mirror cannot be perfect. The laws must have a preference, however slight, however deeply hidden. They must, in some measurable sense, favor matter over antimatter, or treat the two differently enough that the outcomes diverge. And we know this is true. We have seen it. In the quiet decay of unstable particles, in the careful measurements of laboratories on opposite sides of the world, the preference is there. Matter and antimatter do not behave identically. The mirror is not quite right. But, and this is the part that keeps physicists awake, the preference we have measured is not large enough. The CP violation observed in kaons, in B mesons, It is real, and it is confirmed, and it is not nothing. But when you calculate how much asymmetry it could have produced in the early universe, the number falls short, far short. The gap between what we have found and what we need to explain is not a small one. Something is missing. Some source of CP violation that is larger, or different in character, or operating through a mechanism we have not yet identified. It may lie in the behavior of neutrinos, those almost weightless particles that pass through ordinary matter as though it were not there. It may lie in physics beyond what our current theories describe. It may lie somewhere we have not yet thought to look. The second Sakharov condition is satisfied in principle. The universe does treat matter and antimatter differently. We have the evidence, but the degree of difference we have found is not sufficient. The condition is met, but only partially, only faintly. Like a door that is open, just a crack, when what is needed is a door thrown wide. There is something almost meditative about this. The universe left behind a clue, a 1 in a billion excess, written into the structure of everything that exists. And we have been reading that clue for decades, carefully, patiently, with instruments of extraordinary precision. And we have learned a great deal. We have confirmed that the asymmetry is real. We have named it. We have identified the conditions it required. We have found traces of the mechanism in the decay of particles that live for only fractions of a second before dissolving back into energy. And still, the full answer is not there. Not yet. It is as though the universe encoded its own origin story in a language we can almost read. We recognize the letters. We can sound out some of the words, but the grammar of it, the deep structure, the sentence that would make everything clear, that part remains just beyond reach. 1 part in a billion. That is all it was. That is all it needed to be. And somewhere in that almost nothing, in that whisper of asymmetry smaller than any scale we can hold in our hands, the entire history of the cosmos was decided. Every star that has ever burned, every world that has ever turned slowly in the dark, every quiet breath drawn on a night like this one, all of it resting on a difference so small it barely existed at all. And yet, it was enough. There is a third condition, and in some ways, it is the strangest of the three. The processes that changed the balance of matter and antimatter. They could not have happened in a universe that was calm. They could not have happened in a universe that had settled into stillness, where every reaction and its reverse were occurring at exactly the same rate, where everything was in perfect balance. They required a universe in turmoil, a universe out of thermal equilibrium. In the very first moments after the Big Bang, the universe was not in balance. It was expanding too fast, cooling too quickly, changing too rapidly for any kind of equilibrium to take hold. Reactions were running in one direction faster than they could run in the other. And in that brief, violent asymmetry of temperature and time, the conditions existed for something irreversible to happen. For the balance to tip, just slightly, just once, but enough. The third Sakharov condition, then, is this: that the universe was not at rest when the asymmetry was written into it, that the moment of decision, if we can call it that, was a moment of upheaval, a moment when the ordinary rules of equilibrium did not apply. And here is something worth sitting with quietly. All three of these conditions, baryon number violation, CP violation, and departure from thermal equilibrium, all three of them are, in principle, present in the standard model of particle physics, the framework that describes, with extraordinary precision, the behavior of every particle we have ever detected. It contains, within itself, the seeds of all three requirements. And yet, it is not enough. The standard model does predict CP violation. It does allow for processes that could, in principle, tip the balance between matter and antimatter. But when physicists calculate how much CP violation the standard model actually produces, the number they arrive at is far too small. Not slightly too small, not almost enough. Too small, by many orders of magnitude. The asymmetry we observe in the universe, 1 part in a billion, is itself almost nothing. And yet the standard model cannot even account for that almost nothing. The gap between what the theory predicts and what the universe actually contains is vast. It is one of the deepest silences in all of physics, a place where the most successful theory ever constructed simply runs out of words. To understand why this matters, it helps to understand what CP symmetry actually means. CP symmetry is the idea that the laws of physics should look the same under 2 combined transformations. The first is charge conjugation, replacing every particle with its antiparticle, swapping positive charges for negative ones, matter for antimatter. The second is parity, reflecting space itself, as though the universe were viewed in a mirror. If CP symmetry held perfectly, a world made of matter and a world made of antimatter would be indistinguishable. Every process that could happen in one would happen at exactly the same rate in the other. There would be no way, from the inside, to tell which was which. And for a long time, physicists assumed this was true. It seemed natural. It seemed elegant. It seemed like the kind of symmetry the universe would respect. Then, in 1964, 2 physicists at Brookhaven National Laboratory in the United States found that it did not. James Cronin and Val Fitch were studying kaons, unstable particles that form briefly in high-energy collisions before decaying into lighter particles. Kaons come in matter and antimatter versions, and the 2 were expected to decay in mirror-image ways. If CP symmetry held, the rates and patterns of their decay should be identical. They were not. The difference was small, subtle enough that it had gone unnoticed for years. But it was real, and it was measurable, and it meant something profound. It meant that the universe, at the level of its most fundamental particles, does not treat matter and antimatter as perfect equals. There is a preference written into the laws of physics themselves, however faint. Cronin and Fitch published their results, and the physics community absorbed the findings slowly. It was not the kind of discovery that announces itself loudly. It arrived quietly, in the decay patterns of particles that existed for only fractions of a second, but its implications were enormous. If CP symmetry could be violated, if the laws of physics could distinguish, even slightly, between matter and antimatter, then Sakharov's second condition was not merely theoretical, it was real. It had been observed in a laboratory. The universe was not perfectly symmetric after all. Cronin and Fitch received the Nobel Prize in Physics in 1980, 16 years after their discovery. Sometimes the significance of a finding takes time to settle into the understanding of a field. This was one of those times. But even as the discovery was celebrated, a quieter problem remained. The CP violation in kaons was real. It was confirmed. It was precise. And it was nowhere near large enough to explain the matter-antimatter asymmetry of the universe. The difference in decay rates between kaons and their antimatter counterparts was a small fraction of a small fraction. A whisper within a whisper. It pointed in the right direction. It showed that CP violation existed, that the universe was capable of it, but it could not, on its own, account for the 1 in a billion excess that made everything possible. So the question remained open, and it remains open still. The standard model, for all its precision, for all its extraordinary success in describing the particles and forces that make up the physical world, cannot bridge that gap. It contains CP violation, yes, but not enough. Not nearly enough. The theory that describes the electron and the quark and the photon with almost unimaginable accuracy falls silent when asked to explain why the universe exists at all. There is something almost humbling in that. The most carefully constructed, most rigorously tested framework in the history of science, and it cannot answer the most basic question of all. Why is there something rather than nothing? Why did matter survive? Why, in that first fraction of a second, did the balance tip just enough? The standard model points toward the answer. It shows us the shape of the question. It gives us the vocabulary, CP violation, baryon asymmetry, thermal equilibrium, the words we need to even begin asking. But the answer itself lies somewhere beyond it. In physics that has not yet been written, in particles that have not yet been found, in symmetries that are broken in ways we have not yet measured. And so the search continues. Quietly, patiently, in laboratories and detectors and underground chambers where the noise of the world cannot reach. Physicists measuring the decay of particles that live for less than a heartbeat. Looking for the place where the mirror is not quite perfect. Looking for the crack in the symmetry where the light of understanding might eventually come through. 1 part in a billion. That is what they are looking for. That is what they are trying to explain. And somewhere in the mathematics of it, somewhere in the data accumulating slowly in detectors around the world, the answer is waiting. Patient as the universe itself. The search did not begin with grand declarations. It began with careful watching, with physicists sitting with their data, reading the numbers again and again, looking for the place where the symmetry quietly failed. And they found it. Not just once. They found it again. After kaons, the search moved to a different kind of particle, a particle called the B meson, named for the bottom quark it carries inside it. A bottom quark is one of the 6 known varieties of quark, heavier than the up and down quarks that make up ordinary protons and neutrons. The B meson is unstable. As so many particles are, it lives for only about a picosecond before decaying into lighter particles. And in that brief, silent decay, physicists found another place where the mirror was not quite perfect. 2 experiments set out to measure it. One was called BABAR. It ran at a laboratory in California, at a place called SLAC, a long, quiet facility where electrons and their antimatter twins were accelerated toward each other and made to collide. The collisions produced B mesons and their antimatter counterparts in large numbers, and the detectors watched patiently as those particles decayed, counting the differences, measuring the asymmetry. The other experiment was called BELL. It ran in Japan, at a laboratory called Keck, a different detector, a different team, a different country, and yet the same question, asked with the same quiet precision. Both experiments found it. CP violation in B meson decays. Confirmed, measured, recorded with care. The mirror was broken here too. The B meson and its antimatter twin did not decay in exactly the same way. The laws of physics, at this level, did not treat them identically. Matter and antimatter were not perfect reflections of each other. It was a genuine discovery, a real and measurable asymmetry, confirmed independently on opposite sides of the world. And yet, it was not enough. The asymmetry was real, but it was small. And when physicists calculated how much CP violation would be needed to explain why the universe is filled with matter, why anything exists at all, the numbers from kaons and B mesons fell short, not by a little, by many orders of magnitude. The confirmed violations were like finding a single candle when you needed the light of 100 billion suns. The crack in the mirror was there, but it was not wide enough. This is the quiet frustration at the heart of the problem. The standard model does predict CP violation. Experiments have confirmed it, and still, the total effect is far too small to account for what we see around us. For every galaxy, every planet, every grain of dust drifting through the dark between the stars, there is a name for the process that would explain it all: baryogenesis. It is the word physicists use for whatever happened in the early universe to produce the imbalance between matter and antimatter, the process, or collection of processes, that tipped the scales. That allowed one extra matter particle to survive for every billion pairs that annihilated. Baryogenesis is not a single confirmed theory. It is more like a name for a question, a placeholder for the answer that has not yet been fully found. It describes what must have happened, even if the precise mechanism remains uncertain. What we do know is something about when. The universe was very young when it happened. In the first fraction of a second after the Big Bang, the universe was not the cool, dark, mostly empty place it is today. It was something almost impossible to hold in the mind. A dense, seething plasma of particles and energy. Temperatures so extreme that the distinction between matter and radiation barely held meaning. Everything was in motion. Everything was interacting. Everything was changing from one form into another with extraordinary speed. In those first microseconds, millionths of a second, the universe was filled with quarks and gluons, the fundamental building blocks of matter, moving freely, not yet bound into protons or neutrons, and alongside them, their antimatter counterparts, antiquarks and antigluons, identical in mass, opposite in every charge. The two populations existed together in that blazing plasma, colliding and annihilating and being recreated from pure energy in an endless, furious exchange. It was not yet a universe of things. It was a universe of process, of becoming and unbecoming, over and over, faster than any clock could measure. And somewhere in that chaos, the asymmetry was being written. One extra quark for every billion pairs. A preference so slight it would have been invisible against the noise of everything else happening at the same moment. And yet, it was enough. It would turn out to be everything. As the universe expanded, it cooled. The temperature fell. And as it fell, the energy available for creating new particle-antiparticle pairs began to drop below what was needed. The creation slowed. The annihilation continued. And the pairs disappeared, converting back into light, into gamma rays, into pure energy, streaming outward in all directions. All of them gone. Except for the ones that had no partner to meet. The survivors. By the time the universe was about 1 second old, the temperature had dropped far enough that protons and neutrons could no longer be created from pure energy. The window had closed. What remained was what remained. A universe of light and radiation, and the faint residue of matter that had survived the annihilation. 1 second? In the span of a human life, 1 second is almost nothing. A breath half taken. A thought not yet finished. But in the life of the early universe, 1 second was an enormous stretch of time. More had happened in the preceding fraction of a second than would happen in the next several 100,000 years. The quarks had bound together into protons and neutrons. The antimatter counterparts had found their partners and vanished. The great annihilation had swept through the universe like a tide going out, leaving behind only the smallest residue. And that residue, that 1 in a billion excess, was the seed of everything. The protons and neutrons that survived would eventually find each other. They would form the nuclei of the lightest elements: hydrogen, helium, a trace of lithium. Clouds of gas would gather under gravity, slowly, over millions of years. Stars would ignite. Heavier elements would be forged in stellar cores and scattered by stellar deaths. Planets would form from the debris, and on at least one of those planets, in at least one corner of one ordinary galaxy, the matter that survived would arrange itself into something that could look back at the sky and wonder how it came to be here. All of that? From one extra particle in a billion. From a symmetry that was almost perfect. Almost. The word carries so much weight when you hold it quietly. Almost perfect means imperfect. And that imperfection, that barely there asymmetry in the laws of physics, written into the decay of particles that lived for less than a heartbeat, is the reason the universe is not simply a vast, featureless sea of light. It is the reason there is structure. The reason there is matter. The reason there is anything at all to ask questions about. Baryogenesis happened. That much is certain. The evidence is all around us, in every atom of everything that exists. But the precise mechanism, the exact way the laws of physics conspire to produce that 1 in a billion excess, remains one of the deepest open questions in all of science. The experiments confirmed the asymmetry in kaons. They confirmed it in B mesons. And still the full answer lies somewhere beyond what has been measured. Somewhere in physics not yet written. Somewhere in the early universe, in that first blazing second, in the silence before protons existed. The answer is there, waiting, as it has always been waiting, for the right question to find it. And so, the search continues. Not in the abstract, not in the pages of old textbooks, but in the living, ongoing work of experiments that are running right now, in this very moment. As you lie here in the quiet, there is a moment in the early universe that physicists return to again and again. A moment so brief it has no name in ordinary language. It occurred roughly 1 picosecond after the Big Bang, 1 trillionth of a second, a span of time so small that light, traveling at its full and extraordinary speed, would not have crossed the width of a single atomic nucleus. And yet, in that sliver of time, something changed. The universe cooled. Not slowly, the way a cup of tea cools on a table, but in the way that only a universe can cool, rapidly, catastrophically, a temperature drop of unimaginable scale compressed into an instant. And as it cooled, a field that permeates all of space, the Higgs field, settled. Before that moment, the Higgs field had been restless, fluctuating, undecided, in a sense, about the shape it would take. But as the temperature fell through a critical threshold, the field found its ground state, the state it has held ever since, the state that gives particles their mass, that shapes the structure of matter as we know it. This is called the electroweak phase transition. It is the moment when two of the fundamental forces of nature, electromagnetism and the weak nuclear force, separated into the distinct forces we observe today. Before this transition, they were unified, a single electroweak force, operating in a universe too hot for the distinction to matter. After it, they were two, and in the brief, turbulent window around that transition, something else may have happened. Something that left a mark on everything. The Higgs field, as it settled, may have allowed processes that would otherwise be forbidden. Processes that could change the number of baryons in the universe. Processes that, under ordinary conditions, simply do not occur. These are called sphaleron processes. The name comes from a Greek word meaning something like ready to fall, and that image is apt. A sphaleron is not a particle. Exactly, it is a kind of quantum transition, a rare, fleeting rearrangement of the fields that make up the fabric of space. A momentary configuration that sits at the top of an energy barrier, balanced, before tumbling to the other side. And when it tumbles, baryon number changes. In the cold universe we inhabit today, sphaleron processes are essentially impossible. The energy required is enormous, and the temperature of the universe, just a few degrees above absolute zero, on average, provides nothing close to what is needed. They are exponentially suppressed, vanishingly rare, for all practical purposes, absent. But in the early universe, the temperature was not a few degrees above absolute zero. It was trillions of degrees. In that environment, sphaleron processes would have been active, occurring constantly, throughout the hot plasma of the young universe, churning baryon number up and down like a sea in a storm. And if the conditions were right, if CP symmetry was being violated, if the universe was out of thermal equilibrium, then those churning processes might not have been symmetric. They might have produced slightly more matter than antimatter, or preserved a slight excess that had already begun to form. The electroweak phase transition is one of the most studied candidates for the moment when baryogenesis occurred, and it is a genuine candidate. The physics is real. The processes are real. The mathematics is well developed. But as with so much in this story, the standard model's prediction of CP violation is not quite strong enough. The asymmetry it would produce falls short of what we observe. And so, physicists look further. They look earlier. There is another theory, quieter in some ways, more radical in others. It proposes that the asymmetry did not begin with baryons at all. It began with a different family of particles entirely, Leptons. Leptons are the family that includes electrons and neutrinos. They are not made of quarks. They do not feel the strong nuclear force. They are, in a sense, the lighter, more elusive cousins of the baryons. And leptogenesis, the theory named for them, proposes that the matter-antimatter imbalance began here, in this family, before it ever touched the baryons. The idea rests on a particle that has never been directly observed, a very heavy neutrino. The neutrinos we know, the ones produced in the sun, the ones passing through your body in their billions every second, are extraordinarily light, the lightest massive particles known to physics. But some theories predict that these familiar light neutrinos have heavy counterparts, partners, in a sense, of enormous mass. So massive they could only have existed in the extreme heat of the very early universe. In leptogenesis, these heavy neutrinos were created in the first moments after the Big Bang, and then they decayed. Slowly, by the standards of particle physics, but they decayed. And here's the crucial point. They decayed in a way that violated CP symmetry. The heavy neutrino and its antimatter counterpart, the heavy antineutrino, decayed at slightly different rates into slightly different products. Not by much, but by enough. That decay left behind a small excess of leptons over antileptons, a lepton asymmetry, seeded into the young universe like a quiet imbalance in an otherwise even scale. And then the Sphaleron processes went to work. Because Sphaleron processes do not only affect baryons, they connect the baryon number and the lepton number of the universe in a precise mathematical relationship. They can convert a lepton asymmetry into a baryon asymmetry. Slowly, through countless quantum transitions in the hot plasma, the lepton excess was partially converted, transferred, translated into the language of baryons. And the result was the universe we inhabit. 1 part in a billion. Surviving matter. Everything. Leptogenesis is, in many ways, an elegant theory. It explains why the asymmetry is so small, because it began as a small asymmetry in a different sector of physics and was then diluted further through conversion. It connects the mystery of baryogenesis to the mystery of neutrino mass, 2 of the deepest open questions in physics, and suggests they may have a single answer. But it is also, for now, difficult to test directly. The heavy neutrinos that leptogenesis requires would have masses far beyond anything a particle accelerator can currently reach. They lived and decayed in the first fractions of a second after the Big Bang, in conditions that cannot be recreated in any laboratory on Earth. What can be tested is the CP violation in the neutrinos we do have access to, the light ones, the ones that pass through the planet as though it were not there. If the familiar neutrinos violate CP symmetry strongly, if they and their antimatter counterparts behave differently in measurable ways, it would not prove leptogenesis, but it would be consistent with it. It would be a thread, pulled gently, that might lead somewhere deeper. And that thread is being pulled, right now, in experiments buried deep underground. In detectors filled with tens of thousands of tons of ultra-pure water. In beams of neutrinos fired through the solid rock of the Earth, crossing hundreds of kilometers in the dark, arriving changed. The universe left a clue in the asymmetry of its own existence, and the search for that clue continues, patient and precise, 1 measurement at a time. The neutrino is, in many ways, the quietest thing in the universe. It has mass, that much is now certain, but so little of it that physicists still cannot agree on the exact number. The best measurements place the neutrino's mass at least 1,000,000 times smaller than the electron, which is itself already an almost weightless thing. If you tried to imagine the electron as a grain of sand, the neutrino would be something smaller than the finest mist, a presence so faint it barely registers as being there at all. And yet it is there. Everywhere. In fact, hundreds of billions of neutrinos pass through every square centimeter of your body every second, through the blanket, through the mattress, through the floor, through the rock beneath the building, through the planet itself. They do not slow down. They do not notice. The Earth, to a neutrino, is no more substantial than open air. There are three kinds of neutrino that we know of: the electron neutrino, the muon neutrino, and the tau neutrino. Each is associated with a different charged particle, a different corner of the particle family. And for a long time, physicists assumed these three types were fixed, that an electron neutrino, once created, would remain an electron neutrino forever. That assumption turned out to be wrong. Neutrinos, it was discovered, can change. As they travel, they shift from one type to another and back again, cycling through identities in a slow, wave-like rhythm. This process is called neutrino oscillation, and it is one of the stranger things that happens quietly in the fabric of the world. The confirmation came in 1998 from a detector buried deep beneath a mountain in Japan. Super Kamiokande is a vast cylindrical tank filled with 50,000 tons of water so pure it would dissolve the minerals from your skin if you touched it. Its walls are lined with thousands of light sensors, each one waiting for the faint blue flash that a neutrino occasionally produces when it strikes a water molecule. The detector was built to watch for rare events, and in 1998, it found one. Not a single dramatic flash, but a pattern. A careful count of neutrinos arriving from different directions. Neutrinos produced by cosmic rays striking the atmosphere above Japan, above the Pacific, above the far side of the Earth. The ones that had traveled farther, passing through the planet itself, were arriving in smaller numbers than expected. Some of them had changed type during the journey. They had oscillated. And because oscillation requires the different types to have slightly different masses, the conclusion was unavoidable. Neutrinos have mass. It was a quiet revolution. The Standard Model, as it had been written, did not predict this. Neutrinos were supposed to be massless. The discovery meant the model was incomplete, that something had been left out, that the universe was, once again, more intricate than the equations had assumed. And where there is oscillation, there is the possibility of asymmetry. If neutrinos can change type, the question becomes whether they change at the same rate as antineutrinos. Whether a muon neutrino traveling through space transforms into an electron neutrino at the same pace as a muon antineutrino transforms into an electron antineutrino. If the rates are different, if matter and antimatter behave differently even here, in these almost nothing particles, then CP symmetry is violated. That is the question the T2K experiment was built to answer. T2K stands for Tokai to Kamioka. A beam of muon neutrinos is generated at a facility on the eastern coast of Japan, aimed not upward into space, but downward, into the ground, directed at a target 295 kilometers away. The beam passes through solid rock, through the slow geological dark of the Earth's crust, arriving at the Super Kamiokande detector on the other side. Some of those muon neutrinos, during the crossing, will have transformed into electron neutrinos. The detector counts how many. Then the experiment is run again with antineutrinos. A beam of muon antineutrinos, the same distance, the same detector. And the question is whether the count comes out the same. In 2020, T2K published results that drew careful attention from physicists around the world. The numbers were not identical. The neutrinos appeared to oscillate more readily than the antineutrinos. More of the muon neutrinos had transformed into electron neutrinos than the corresponding antineutrinos had. The difference was not yet large enough to be called a definitive discovery. The statistical confidence fell short of the threshold physicists require before declaring something certain, but it was a strong hint. A lean in one direction. The kind of result that does not settle a question, but sharpens it. If that asymmetry is real, if future measurements confirm it with greater precision, it would mean that neutrinos violate CP symmetry, that the laws governing these near weightless particles treat matter and antimatter differently, and that difference, however small it seems in a laboratory, would point back toward the earliest moments of the universe, toward the conditions in which leptogenesis might have unfolded. It would not be proof. The connection between the CP violation measurable in today's light neutrinos and the CP violation that would have driven leptogenesis in the very early universe is not direct. The heavy neutrinos of leptogenesis are gone, unreachable, but the light neutrinos carry, in their behavior, an echo of the same underlying physics, a family resemblance. If CP violation is present in the neutrinos we can study, it suggests that CP violation was present in the neutrinos we cannot, the massive, short-lived ones that decayed in the first fractions of a second and left behind the seeds of everything. The universe, after all, began in near-perfect balance. For every particle of matter that formed from the cooling energy of the Big Bang, an antiparticle formed alongside it. They were twins, identical in mass, opposite in charge, destined to find each other and vanish. And almost all of them did. The annihilation was vast and total, a conversion of almost everything back into light. What remained was the remainder. One particle in every billion pairs that had no twin to meet. One particle that survived not because it was special, but because the symmetry was not quite perfect. That imperfection is everything. Every star that burns in the night sky is made of it. Every planet that formed from cooling dust, every ocean that gathered in a basin of rock, every cell that learned to divide and grow and remember. All of it traces back to that 1 in a billion excess, to a difference so small it is almost not a difference at all. And the neutrino, this near-nothing particle, this ghost that passes through the world without leaving a mark, it may carry the explanation. Not loudly, not in a way that announces itself, but in the quiet asymmetry of its oscillations, in the slightly different rates at which it and its antimatter counterparts shift from one identity to another. There may be a reflection of why the universe exists as it does, why there is matter at all, why there is something rather than nothing. The measurements continue. The detectors wait in their underground chambers, patient and cold and still. The beams of neutrinos cross the dark interior of the Earth, arriving changed, being counted, being compared, each result a small step, a narrowing, a thread pulled a little further from the tangle. The answer is not yet in hand, but the question has never been asked more precisely than it is being asked right now. And that precision is about to deepen. A new detector is being built in the mountains of Japan. Hypercamiocand, the successor to the experiment that first confirmed neutrino oscillation a quarter century ago. It will be filled with roughly 260,000 tons of ultra-pure water, instrumented with thousands of light sensors, buried beneath rock and silence. When it is complete, it will watch neutrinos and antineutrinos arrive from a beam fired hundreds of kilometers away, and it will compare them with a steadiness and resolution that no instrument before it has achieved. The question it is asking is the same question that has threaded through all of this. Do neutrinos and antineutrinos behave differently from one another? And if they do, how differently? The hints are already there, quiet and suggestive. Hypercamiocand will listen more carefully. On the other side of the world, a different experiment is taking shape. DUNE, the Deep Underground Neutrino Experiment, will send a beam of neutrinos from a laboratory in Illinois, eastward through the solid rock of the Earth's crust, for 300 kilometers, to a detector buried nearly a mile underground in South Dakota. The detector will be filled with liquid argon, cooled to temperatures far below anything that occurs naturally on the surface of this planet, and it will catch the neutrinos as they arrive, altered by their long passage, and measure what they have become. 300 kilometers through the Earth, not through air, not through water, through rock and mantle, and the slow, dark interior of a continent. The neutrinos will not notice. They pass through matter as though it were not there, as though the mountain and the crust and the deep stone were simply open space. And yet, the journey changes them in ways that depend on their nature, on whether they are matter or antimatter, on the subtle asymmetry that may or may not be written into their physics. Both experiments, one in Japan, one threading beneath North America, are asking the same quiet question from different angles. Together, they may finally give a clear answer. Or they may find something unexpected entirely. That, too, is part of the work. But to understand why any of this matters, it helps to go back, not to the early universe, but to a desk in Cambridge in the year 1928. A young physicist named Paul Dirac was attempting something that had not been done before. He was trying to write a single equation that obeyed both quantum mechanics and special relativity at the same time. Quantum mechanics described the behavior of particles at very small scales. Special relativity described how objects behave when moving close to the speed of light. The two theories had been developed separately, and combining them was not straightforward. Dirac found a way. His equation described the electron with remarkable accuracy. It predicted properties of the electron that had been measured in laboratories, and it did so with a precision that earlier equations could not match. But the equation had a peculiarity. It had two solutions. One solution described the electron as physicists knew it, a particle with a certain mass, a certain negative charge, moving through space in the ways electrons move. The other solution describes something else, a particle with the same mass as the electron, but with the opposite charge, positive instead of negative. Everything else identical. Dirac was cautious about what this meant. For a time, he wondered whether the second solution might correspond to the proton, the only other particle then known. But the mathematics would not allow it. The proton is nearly 2,000 times heavier than the electron, and the equation required the two solutions to have equal mass. The second solution, it seemed, described a particle that did not yet appear in any catalog of known things. Dirac proposed, quietly and carefully, that it might be real, that nature might contain a mirror particle for the electron, identical in every way except for the sign of its charge. He called it, at first, an anti-electron. The idea was met with some skepticism. It was a strange thing to propose, a particle that had never been seen, predicted not from experiment, but from the internal logic of an equation. And then, 4 years later, it was seen. Carl Anderson was a young physicist at the California Institute of Technology, studying cosmic rays, the streams of high-energy particles that arrive continuously from space, striking the upper atmosphere of the Earth. He was using a cloud chamber, a device that makes the paths of charged particles visible as thin trails of condensation in a supersaturated vapor. A magnetic field bent the trails, and from the direction and curvature of the bend, Anderson could determine the charge and momentum of whatever had passed through. In 1932, he observed a track that curved the wrong way. It had the curvature of an electron, the same mass, the same behavior, but it bent in the direction that a positively charged particle would bend. It was not a proton. The track was too light for that. It was something with the mass of an electron and the charge of a proton. It was Dirac's anti-electron. Anderson called it the positron. The first piece of antimatter ever directly observed, predicted by mathematics, confirmed by a thin white line in a cloud of vapor. It was a quiet discovery in its physical appearance, just a curved trace, a ghost of a path left in condensing droplets. But what it meant was not quiet at all. It meant that for every particle in nature, there might exist a counterpart, an antimatter twin, identical in mass, opposite in charge, annihilating on contact. The universe, it turned out, had a mirror. And that mirror is not entirely absent from the world around us. Even now, as you rest, cosmic rays are striking the upper atmosphere of the Earth. High-energy protons and heavier nuclei, arriving from distant sources across the galaxy, collide with atoms in the air far above the surface. Those collisions produce cascades of secondary particles, pions, muons, electrons, and among them, positrons, antimatter, created continuously, high above the clouds. Most of those positrons do not last long. They encounter electrons almost immediately, and the two annihilate, producing gamma rays that disperse into the atmosphere. The antimatter is created and destroyed in moments, leaving no lasting trace. But it is there, arriving from space, flickering briefly into existence, vanishing again. A small and constant reminder that the universe knows how to make antimatter, that the process has not stopped, that the physics which governed the first moments after the Big Bang still operates, in miniature, in the sky above, a sleeping world. The positron that Anderson saw in 1932 was one of these, born in a cosmic ray collision somewhere above California, curving through his cloud chamber, leaving its brief signature, and then gone. It took 4 years from Dirac's prediction to Anderson's observation. 4 years from an equation on a page to a line in a cloud of vapor. That is, in the history of physics, a remarkably short time. And what those 4 years contained, the prediction, the doubt, the discovery, is a small version of the larger story that is still unfolding. The story of antimatter, of why it exists, of why there is so little of it left, of what the difference between matter and antimatter ultimately means. The equation came first, then the particle, and the question of why the universe chose one over the other, why matter survived and antimatter did not, that question is still open, still being asked. Still, somewhere in the dark and the quiet, being answered. And yet the story did not end in 1932. The positron Anderson discovered was real, was measurable, was there in the vapor of his cloud chamber, and then it was gone, annihilated, converted back into light the moment it met an ordinary electron. That is what antimatter does when it encounters matter. It does not persist. It vanishes, completely and immediately, leaving only energy behind. And we have learned to use that. In hospitals, quietly, every day, there are machines that rely on exactly this process. A small amount of a radioactive substance is introduced into the body. As it decays, it releases positrons, antimatter electrons, each one identical to what Anderson saw, each one born from a nucleus shedding energy in the only way it can. Those positrons travel a very short distance through tissue, a few millimeters at most, and then they meet an ordinary electron, and both are annihilated, converted into 2 gamma rays, traveling in precisely opposite directions. The machine detects both rays simultaneously, and from that coincidence, from the fact that 2 photons arrived at opposite sides of the detector at the same instant, it can calculate exactly where the annihilation occurred. It can map the interior of a living body with a precision that would have seemed impossible a century ago. Positron emission tomography, a medical technology built entirely on antimatter annihilation, on the same physics that emptied the early universe of almost everything it contained. There is something quiet in that, something worth sitting with. The process that nearly erased all structure from the cosmos, that converted matter and antimatter alike into pure light, is also the process that lets a physician see a tumor forming or watch a brain responding to thought. The same annihilation, the same gamma rays, only now contained, measured, turned toward understanding. But the hospitals are not where the deepest questions are being asked. Those questions are being asked underground, and in long tunnels, and in places where the air is kept very still and the temperature is kept very cold. Places where physicists are not using antimatter to image the body, but to compare it carefully, patiently, with matter itself. At CERN, the Large Particle Physics Laboratory near Geneva, there is an experiment called ALPHA. Its purpose is to make antihydrogen and to hold it. Antihydrogen is exactly what the name suggests. It is the antimatter version of the simplest atom in the universe. An ordinary hydrogen atom consists of 1 proton at its center, with 1 electron moving around it. Antihydrogen replaces each of those with its antimatter counterpart, 1 antiproton at the center, 1 positron moving around it. The mirror image, in every measurable sense, of the most abundant atom in the cosmos. Making antihydrogen is not simple. The antiprotons must be slowed from the enormous speeds at which they are produced, cooled to temperatures close to absolute zero, and then brought together with positrons in conditions precise enough that they can combine. The whole process is delicate in a way that is difficult to convey. A single stray magnetic field, a single collision with an ordinary atom, and the antihydrogen is gone, annihilated before it can be studied. And even when it is made, it cannot be allowed to touch anything. Antihydrogen held in a container made of ordinary matter would annihilate the moment it reached the walls. So it is held instead by magnetic fields, suspended in a kind of invisible cage, kept away from everything that would destroy it. The alpha experiment has held antihydrogen atoms for up to 1,000 seconds. That is not quite 17 minutes. In the context of a human life, it is nothing. In the context of antimatter physics, it is a very long time, long enough to study. And what the physicists at Alpha are studying is the light that antihydrogen emits. When an electron in a hydrogen atom absorbs energy, it moves to a higher energy level. When it releases that energy, it falls back down, and the energy leaves as a photon, a particle of light at a very specific wavelength. The pattern of wavelengths that hydrogen emits is called its spectrum, and it is one of the most precisely measured things in all of science. Every hydrogen atom in the universe emits the same pattern, the same lines, at the same frequencies without variation. If antihydrogen is truly the mirror image of hydrogen, if the laws of physics treat matter and antimatter with perfect symmetry, then antihydrogen should emit exactly the same spectrum, the same lines, the same frequencies, indistinguishable. So far, that is what the measurements show. The energy levels of antihydrogen match those of hydrogen to within the precision that current instruments can achieve. That result is, in one sense, reassuring. It suggests that the basic structure of the atom, the relationship between a nucleus and the particle orbiting it, does not depend on whether those particles are matter or antimatter. The physics is the same. But in another sense, it deepens the mystery. Because if matter and antimatter are truly identical in their properties, if every measurement confirms their symmetry, then the question of why the universe contains so much more of one than the other becomes harder, not easier, to answer. The symmetry being tested here has a name. It is called CPT symmetry. The letters stand for three separate operations: charge conjugation, which swaps particles for antiparticles; parity, which mirrors space; and time reversal, which runs the clock backward. CPT symmetry is the statement that if you perform all three of these operations simultaneously, the laws of physics remain unchanged. It is not a hypothesis that physicists arrived at by experiment. It is a consequence, a deep mathematical consequence, of the framework that underlies all of modern physics. Quantum field theory, the language in which the standard model is written, requires CPT symmetry. It is not optional. It is built into the structure of the theory at a level so fundamental that violating it would require not just a new discovery, but a reconstruction of the foundations. No experiment has ever detected a violation of CPT symmetry. Not one. Every measurement ever made of particles and antiparticles, of their masses, their charges, their magnetic properties, their spectral lines, has been consistent with CPT symmetry holding exactly. And yet, the universe exists. Matter exists. You exist. And the only reason any of that is true is that somewhere, in the first moments after the Big Bang, something treated matter and antimatter differently. Something broke a symmetry. Something introduced an imbalance so small, 1 part in a billion, that it is almost nothing, and yet it is everything. The physicists at Alpha are looking for that something. They are measuring the spectrum of antihydrogen with increasing precision, narrowing the uncertainty, pushing the comparison between matter and antimatter to levels that were not possible a decade ago. They are not expecting to find a difference, but they are looking, because the alternative, assuming the symmetry is perfect without checking, is not how physics works. The answer, if it is there, will not announce itself loudly. It will appear as a small discrepancy, a line in a spectrum that falls at a slightly different frequency than expected, a number that does not quite match, something almost imperceptible. The same kind of almost imperceptible difference that, once, in the very early universe, was enough to change everything. And so the search continues, quietly, in other forms. There is another experiment at CERN, not far from where Alpha does its work. It is called BASE, the Baryon-Antibaryon Symmetry Experiment, and it approaches the same deep question from a different angle. Instead of measuring the light that antihydrogen emits, BASE measures something called the magnetic moment of the antiproton. The magnetic moment is a property that describes how a particle responds to a magnetic field. Every proton has one. Every antiproton should have one of equal magnitude, opposite in sign if CPT symmetry holds. BASE has measured that property with extraordinary care. The precision they have reached is 1.5 parts per billion. Let that settle for a moment. 1.5 parts per billion. That is a measurement so fine that it is difficult to find an everyday comparison that does it justice. It is the kind of precision that requires years of work, instruments cooled to temperatures near absolute zero, and a patience that most endeavors do not ask of the people who pursue them. And the result? The antiproton's magnetic moment matches the proton's. Within the uncertainty of the measurement, they are the same. CPT symmetry holds, again, to the limits of what can currently be seen. This is the pattern that runs through all of these experiments. Every time physicists look, with whatever instrument they have, at whatever property they can measure, the symmetry holds. Matter and antimatter appear, to every test, so far devised, to be perfect mirrors of each other. And yet, the universe is not symmetric. The universe is made of matter. The mirror was broken, somewhere, somehow, and no one has yet found the crack. This is not a failure of science. It is simply where the frontier is. CPT symmetry is now one of the most precisely tested principles in all of physics. Not because physicists were certain it was true, but because they kept checking and it kept passing every test. That is how trust is built in physics, not through assumption, but through repeated, careful measurement. Still, the question remains open, and the experiments continue. There is something worth pausing on. When thinking about antimatter research, something that gives a quiet sense of just how rare and delicate this work is. Producing antimatter is extraordinarily difficult, not just technically, but energetically. To create 1 gram of antimatter, a quantity you could hold between 2 fingers, would require more energy than all of humanity currently generates, across all its power plants and all its fuel, over the course of several years. 1 gram. The entire global output of human civilization, sustained for years, would not be enough. This is not an engineering limitation that better technology will easily overcome. It is a reflection of how antimatter is made. Creating it requires accelerating particles to enormous energies and colliding them, coaxing antimatter into existence from pure kinetic energy. The process is inherently inefficient because most of the energy goes elsewhere, and even when antiparticles are produced, they must be caught before they touch ordinary matter and annihilate. The largest amount of antihydrogen ever assembled at one time, the most that has ever existed in a controlled setting, in all of human history, is measured in the thousands of atoms. Thousands of atoms. A grain of ordinary sand contains roughly 10 million billion atoms. The entire stock of antihydrogen ever tracked by physicists would be invisible, not just to the naked eye, but to any optical instrument. It would leave no shadow. It would weigh nothing that any scale could register. It exists, in a sense, only as a fact recorded by detectors. And yet, from those thousands of atoms, physicists have extracted measurements of extraordinary precision. They have compared the light of antihydrogen to the light of hydrogen. They have probed the magnetic properties of antiprotons. They have tested the symmetry of the universe using quantities of antimatter so small they border on the philosophical. This is one of the quieter achievements of modern physics, not the discovery of a new particle, not the confirmation of a dramatic prediction, but the patient accumulation of measurements from almost nothing, in pursuit of an answer that has not yet arrived. The Standard Model, for all its precision, does not provide that answer. The CP violation it predicts is real. It has been measured in kaons, in B mesons, and hinted at in neutrinos. But it is not enough. The asymmetry it can account for falls short of the observed imbalance by many orders of magnitude. Something is missing. Physicists have not been idle in the face of that gap. Over the decades, many extensions to the Standard Model have been proposed. Theories that reach beyond what is currently known into territory that has not yet been confirmed by experiment. One of the most studied is supersymmetry. Supersymmetry is a theoretical framework that proposes a kind of deeper symmetry in nature, one that pairs every known particle with a heavier partner. The electron would have a partner called the selectron. The quark would have a partner called the squark. The photon would have a partner called the photino. Each known particle, a shadow partner waiting to be found. If supersymmetry is correct, these partner particles could introduce new sources of CP violation, sources strong enough, in principle, to account for the matter-antimatter imbalance that the Standard Model cannot explain. They could provide the missing ingredient that baryogenesis requires. It is a compelling idea, and for many years, it was considered one of the more promising paths forward. But the Large Hadron Collider at CERN, the most powerful particle accelerator ever built, has been searching for supersymmetric particles for years, and so far, none have been found. The energies at which they were expected to appear have been explored, and the searches have come back empty. This does not mean supersymmetry is wrong. The theory has many forms, and some of them place the partner particles at energies beyond what the LHC can currently reach. The absence of a discovery is a constraint, not a refutation. The door is narrower than it was, but it has not been closed. Other theories remain. Other possibilities have not yet been tested. The space of ideas is still wide, even as experiments continue to map its edges. What is clear is that the answer, whatever it turns out to be, will require something beyond what is currently known. New particles, perhaps, new interactions, new symmetries, or new ways in which existing symmetries are broken. The Standard Model is not the end of the story. It is a chapter, a very precise and well-tested chapter, but not the last one. And so, the work continues. In the cold quiet of underground laboratories, in the hum of superconducting magnets, in the careful analysis of data collected over years, physicists are narrowing the question, even when they cannot yet answer it. Each measurement that confirms CPT symmetry is not a disappointment, it is information. It tells the theorist where the answer is not, which is its own kind of progress. The universe began with a symmetry that was almost perfect. Almost. That single word contains everything. Every galaxy that formed from cooling gas, every star that ignited in the dark, every planet that gathered itself from dust and ice, every living thing that arose on at least one of those planets. All of it rests on that one small word. Almost. The symmetry was almost perfect, and in the space between almost and exactly, the universe found room to exist. There is a theory that has lived at the edge of particle physics for decades now. It is called supersymmetry, and it begins with a kind of mathematical elegance, the idea that for every particle we know, there exists a heavier partner, a shadow particle, waiting to be found. The electron would have its selectron, the quark, its squark, the photon, its photino, each known particle paired with something heavier, something that has not yet shown itself in any detector. Supersymmetry is not a small idea. It would, if true, resolve several deep tensions in physics at once. It would help explain why the Higgs boson has the mass it does. It would offer a candidate for dark matter. And crucially, it would introduce new sources of CP violation, the kind of asymmetry between matter and antimatter that the Standard Model alone cannot provide in sufficient quantity. This is why physicists have wanted it to be true. not out of wishful thinking, but because the mathematics pointed somewhere, and that somewhere looked like it might contain the answer to why matter survived. The Large Hadron Collider at CERN was built, in part, to look. It accelerates protons to within a fraction of the speed of light and collides them with energies that briefly recreate conditions not seen since the earliest moments of the universe. The detectors surrounding those collision points are among the most complex instruments ever constructed. Layers of sensors, each designed to catch a different kind of particle, each recording millions of events per second. And in all of that data, no supersymmetric particles have appeared. Not yet. The LHC has not found them at the energies it has explored so far. This does not mean they do not exist. It means that if they do exist, they are heavier than the collider can currently reach, or they interact in ways that make them harder to see than expected. The absence is not a refutation. It is a constraint. The space of possibilities has grown smaller. Some versions of supersymmetry have been ruled out, others remain. The theory has been pressed, and it is bent, but it is not broken. And so it continues as a candidate, not confirmed, not eliminated, but waiting, as so many things in physics wait, for an instrument precise enough to settle the question. This is how science moves at its frontier. Not in sudden revelations, but in the slow accumulation of limits. Each experiment saying, not here, not this way, not at this energy, until eventually the answer is cornered, and there is nowhere left for it to hide. And while the search continues underground, in tunnels and detectors and beams of accelerated particles, there is another question that looks outward rather than inward. What if the asymmetry is not universal? What if, somewhere beyond what we can see, there are regions of the universe where antimatter won? It is not an unreasonable thought. The observable universe is vast, but it is not the whole universe. The full extent of what exists beyond our cosmic horizon, the boundary set by the finite speed of light and the finite age of time, is unknown and may be unknowable. Some cosmological models allow for the possibility that the matter-antimatter imbalance played out differently in different regions, that the same physics, under slightly different initial conditions, could have tipped the other way. In those distant regions, if they exist, the stars would burn just as steadily, the galaxies would spiral just as slowly, but the atoms would be antiprotons and positrons rather than protons and electrons. Everything would look the same from the inside, and from the outside, there would be no way to tell, unless the two regions met. At the boundary between a matter-dominated region and an antimatter-dominated region, particles and antiparticles would collide and annihilate. The boundary itself would glow, not with ordinary light, but with gamma rays, the high-energy radiation produced whenever matter and antimatter destroy each other. It would be a seam of annihilation, burning quietly at the edge of two incompatible worlds. Astronomers have looked for those seams. The Integral Space Telescope, a gamma-ray observatory operated by the European Space Agency, surveyed the sky with careful attention to the energies that annihilation produces. It looked for the signature glow that a matter-antimatter boundary would leave, a diffuse brightness at the edges of large structures, a pattern that could not be explained by ordinary astrophysical processes. It found nothing of that kind. Within the observable universe, a sphere of space roughly 93 billion light-years across, there is no evidence of large antimatter regions pressing against matter regions, no annihilation boundaries, no unexpected gamma-ray horizons. The observable universe, as far as every instrument has been able to determine, is made entirely of ordinary matter. Every galaxy in the catalogs, every cluster of galaxies mapped by surveys spanning decades of observation, every wisp of intergalactic gas detected in absorption against distant quasars, all of it matter. The antimatter, if it exists in large quantities anywhere, is beyond the reach of any signal that could ever reach us. And so the question of whether antimatter domains exist remains open in a particular way, not because evidence points toward them, but because the observable universe is finite and what lies beyond it is genuinely beyond knowing. The absence of a gamma-ray signal tells us that any large antimatter region must be very far away, farther than the light travel distance of the universe's age could bridge, but it cannot tell us what lies beyond that horizon. This is one of the stranger edges of cosmology, the place where the question is not just unanswered, but, in a precise sense, unanswerable with any instrument we could ever build. The universe may be infinite. It may contain regions we will never see and never communicate with. And in those regions, the story of matter and antimatter may have ended differently. Or it may not. The asymmetry may be universal, written into the laws of physics themselves, not into initial conditions, so that wherever the universe began, matter would always have won by that same 1 in a billion margin. That would mean the antimatter domains do not exist, that the observable universe is not a lucky patch, but a representative sample of something that extends in the same way, matter all the way down, in every direction, without end. No one knows which of these is true. What is known is this: the universe we can see, in every direction, to the farthest distances our instruments can reach, is made of matter. The 93 billion light-years of space that light has had time to cross since the beginning. All of it. Matter. Stars and gas and dust, and the quiet dark between them, all built from the particles that survived. That survival was not guaranteed. It required a departure from perfect symmetry, small enough to be almost invisible, large enough to change everything. One extra particle for every billion pairs, a remainder left over after the annihilation had run its course. And from that remainder, across hundreds of millions of years, gravity gathered what was left. Clouds of hydrogen collapsed, stars ignited, heavier elements were forged in stellar cores and scattered by stellar deaths. Planets formed, and on at least one of them, the matter that survived arranged itself into something that could ask why it was here. The question is still open. And the universe, patient as it has always been, holds the answer somewhere inside itself. There is something else woven through the universe, something that does not shine and does not absorb light and has never been directly touched by any instrument we have built. It is called dark matter. And it is worth pausing here, because dark matter is sometimes confused with antimatter. The two sound as though they might be related, as though one might be the shadow of the other. They are not. Antimatter is the mirror image of ordinary matter, carrying opposite charge, annihilating on contact. Dark matter is something else entirely, something whose nature, even now, remains genuinely unknown. What we know about dark matter comes almost entirely from what it does rather than what it is. It bends light as that light passes through space. It holds galaxies together, providing far more gravitational pull than the visible stars and gas alone could account for. Without it, galaxies as we know them would not hold their shape. They would drift apart, unbound. Dark matter makes up roughly 27% of the total energy content of the universe. And yet it has never been directly detected. No particle detector has ever registered its touch. No telescope has ever caught its glow, because there is no glow to catch. Some physicists have wondered whether dark matter might be connected to the matter-antimatter story, not as antimatter itself, but as something that played a role in the same early chapter. One proposal involves a kind of particle called a sterile neutrino. The three neutrinos we know, the electron neutrino, the muon neutrino, the tau neutrino, interact with ordinary matter, though only barely. A sterile neutrino would interact even less. It would pass through everything, leaving no trace, coupling to the rest of the universe only through gravity. If sterile neutrinos exist and were produced in the early universe, they might account for some or all of the dark matter we infer from gravitational measurements. And because they are a kind of neutrino, they might also have decayed in CP-violating ways in those first moments, seeding the lepton asymmetry that eventually became the matter excess we live inside. It is a theory that connects two mysteries at once. That kind of economy is appealing to physicists. Whether it is true is another question, and one that experiments have not yet answered. What we can say is this: the matter we can see, every star cataloged, every galaxy mapped, every cloud of gas traced by radio telescopes, every grain of dust drifting between the stars, all of it together makes up only about 5% of the universe's total energy content. 5%? The rest is dark matter, and something stranger still, a kind of energy woven into the fabric of space itself, which drives the universe's expansion, and which we understand even less. So when we speak of the matter-antimatter asymmetry, when we speak of the 1 in a billion excess that made everything possible, we are speaking of the origin of that 5%, the thin, bright layer of the universe, the part that burns and cools and clumps and forms in rare and quiet places, becomes alive. All of it, every atom of it, is a survivor. That word carries weight here, and it is worth sitting with for a moment. In the first fractions of a second after the Big Bang, matter and antimatter were created together in almost perfect balance. For every particle of matter, a particle of antimatter. And for every pair, annihilation. Both particles converted back into light, into gamma rays, into pure energy, gone. This happened across the entire universe, simultaneously, at temperatures and densities we have no everyday comparison for. The annihilation was nearly total. For every billion pairs that met and destroyed each other, there was one particle left over, not because it was special, not because it was protected, simply because the laws of physics, in some way we do not yet fully understand, were not quite perfectly symmetric. They favored matter by the smallest possible margin, and that margin was enough. One particle in a billion. That is what remained when the annihilation had run its course. And from those survivors, everything. Every atom in your body carries that history. The oxygen moving quietly through your blood right now, the calcium and the structure of your bones, the carbon that forms the long chains of molecules in every cell. All of it traces back to that 1 in a billion remainder. The iron at the center of a dying star, compressed and fused in the final hours before the star collapses. That iron began as a proton that survived the first second of the universe. The carbon in a living cell folded into the architecture of a protein, doing the slow chemical work of life. That carbon was forged in a stellar core, scattered by a stellar death, gathered by gravity into a new world, and eventually arranged by processes we are still mapping into something that breathes. The silicon in a grain of sand on a quiet shore, catching the last of an evening's light. That silicon was made in a star that no longer exists, from matter that survived an annihilation that happened nearly 14 billion years ago. All of it, every atom of the visible universe, descended from that imperfection. Physicists sometimes say that the question of why matter survived is the most important unanswered question in all of physics. That is a careful claim made by people who do not use words carelessly. There are many open questions in physics: the nature of dark matter, the behavior of gravity at quantum scales, the origin of the universe itself. But the matter-antimatter asymmetry sits at a particular intersection. It is not just a question about particles. It is a question about why anything exists at all. If the asymmetry had been zero, if the laws of physics had been perfectly symmetric between matter and antimatter, the universe would have annihilated itself completely in its first moments. There would be no protons, no neutrons, no atoms, no stars, only light, expanding and cooling forever through an empty space. No structure, no chemistry, nothing that could ask the question. The fact that the question can be asked at all is a consequence of the asymmetry. The existence of the questioner depends on the answer, and the answer is not yet known. Not because the question has been neglected. Generations of physicists have worked on it, built experiments for it, devoted careers to it. The Sakharov conditions were written down more than 50 years ago. CP violation was discovered in 1964. Baryogenesis has been studied from every theoretical angle the Standard Model allows. And still the numbers do not add up. The CP violation we have measured, in kaons, in B mesons, in the hints emerging from neutrino experiments, is real, but it is not enough. The Standard Model, as precise and powerful as it is, does not contain enough asymmetry to explain the universe we live in. Something is missing. Some piece of physics that has not yet been written down, or not yet confirmed, or not yet even imagined clearly enough to test. The universe exists because of an imperfection so small it took decades of careful measurement just to confirm it was real. And the origin of that imperfection remains, for now, one of the deepest silences in science. A silence that is not empty. It is full of experiments running in the dark, detectors waiting patiently underground, beams of neutrinos crossing hundreds of kilometers of solid Earth, and minds turning the question over slowly, from every angle, looking for the place where the answer might come through. That silence has a particular quality to it. It is not the silence of a question that has been forgotten. It is the silence of a question that has been asked, carefully, in dozens of languages, by thousands of people, across more than half a century, and has not yet answered back. Not because the asking stopped, because the answer lives somewhere beyond the edge of what we currently know how to measure. That is a rare kind of not knowing. Most open questions in science are open because no one has looked closely enough yet. This one is open because looking closely has revealed, with great precision, exactly how much we do not understand. The experiments have been done, the measurements have been made, and what they show, quietly and without ambiguity, is that the physics we have is not the physics we need. There is more to find. And that is not a failure. It is a direction. Each generation of experiments does something patient and important. It narrows the space. It rules things out. A theory that once seemed possible gets tested, and the numbers do not fit, and a door closes. Not with drama, but with the soft, definitive click of a measurement that will not change. And somewhere nearby, almost always, another door opens. A new constraint points toward a new possibility. A null result reshapes the question into something more precise, more answerable, more ready to be solved. This is how physics moves, not in sudden leaps, but in the slow, steady narrowing of what remains possible. The Large Hadron Collider searched for supersymmetric particles, the heavier partner particles that some theories predicted would carry enough CP violation to explain the asymmetry. It did not find them, not at the energies it reached. That closed something. It told physicists where the answer is probably not hiding, and that knowledge, quiet as it is, has value. It redirects attention. It sharpens the question. The neutrino experiments continue their patient work. A beam of particles, fired through hundreds of kilometers of solid rock, arrives at a detector and is counted. The difference between how neutrinos behave and how antineutrinos behave, measured over years of accumulated data, may yet reveal a CP violation strong enough to matter. The hint is there. The precision is not yet sufficient, but the detectors are growing larger, and the beams are growing more intense, and the years of data are accumulating like sediment, layer by quiet layer. Somewhere in those numbers, the answer may already be present, waiting for enough data to rise above the noise. And then there is the antimatter itself, held, briefly, in traps at laboratories, measured with instruments of extraordinary delicacy. Antihydrogen, one antiproton circled by one positron, suspended in magnetic fields and illuminated with light. Its spectrum compared, line by line, to the spectrum of ordinary hydrogen. So far, they match. Every measurement consistent with a universe that treats matter and antimatter identically at the level of individual atoms. And yet the universe itself does not treat them identically. The asymmetry is real. It happened. The discrepancy between what the measurements show and what the universe is must live somewhere not yet reached by the instruments. The search continues because the question demands it. Consider what is actually at stake in this question, not in an abstract sense, but in the most concrete sense possible. At the moment of the Big Bang, energy poured into existence and became particles, matter and antimatter, born together in numbers so nearly equal that the difference was smaller than 1 part in a billion. For every billion pairs that formed and annihilated, flashing briefly into gamma rays and vanishing, there was 1 particle left over. Just 1. A single matter particle, unclaimed, with no antimatter twin to meet. 1 in a billion. And then the annihilation swept through. A universe of fire and light, matter and antimatter finding each other and erasing each other, pair by pair, until almost nothing remained. The gamma rays spread outward, the energy dispersed. And what was left? The residue? The remainder, the 1 in a billion survivors, began, slowly, over hundreds of millions of years, to gather. Gravity pulled the survivors together. Clouds of hydrogen condensed. The first stars ignited. Heavier elements were forged in stellar cores and scattered by stellar deaths. Galaxies assembled themselves across hundreds of millions of light years. Planets formed around ordinary stars. And on at least one of those planets, in at least one warm and sheltered place, the matter that had survived arranged itself into something that could ask why it had survived. All of that, every star in every galaxy, every grain of dust drifting between them, every ocean and mountain and living cell, traces back to that 1 in a billion excess, to a symmetry that was almost perfect. Almost. The universe's existence is, in a precise and literal sense, the consequence of an imperfection, not a large imperfection, not a dramatic one, a whisper of asymmetry, smaller than anything we can easily hold in the mind. 1 extra particle for every billion that vanished, and from that whisper, everything. The iron at the center of a star, the carbon woven into every living thing, the silicon in a grain of sand on a beach that formed from the remnants of ancient rock. All of it descended from that 1 in a billion remainder. All of it here because the symmetry was not quite perfect. There is something quietly extraordinary in that. Not extraordinary in a way that demands a response, just extraordinary in the way that certain true things are when you hold them gently and let them settle. The universe did not have to exist. If the laws of physics had been perfectly symmetric, if matter and antimatter had been created in exactly equal numbers, with no preference, no tilt, no deviation, the annihilation would have been total. The gamma rays would have spread through an empty cosmos. No structure would have formed. No stars, no planets, no slow accumulation of complexity over billions of years. Nothing. And yet here is the light from a distant star, traveling for thousands of years to reach a sky above a sleeping world. Here is the weight of a body at rest, the slow rhythm of breath, the warmth of a blanket. All of it matter. All of it descended from survivors. The question of why those survivors existed, why the symmetry broke, why the laws of physics tilted, however slightly, toward matter remains open. It is open not because the question has been neglected, but because the answer requires physics that has not yet been fully written, new particles, perhaps not yet detected, new symmetry violations, not yet measured with sufficient precision, new theoretical frameworks, not yet imagined clearly enough to test. The search continues in places built for patience. In tunnels carved deep into mountains, where the rock above filters out the noise of the surface world and leaves only the faint signals that matter. In vast tanks of ultra-pure water, so clear that a single particle passing through leaves a trace of light that sensitive instruments can read. In beams of neutrinos, fired through the crust of the Earth itself, crossing more than 1,000 kilometers of solid rock to arrive at detectors waiting on the other side. Patient work. Unhurried work. The kind of work that does not announce itself, but accumulates year by year, measurement by measurement, into something that may one day be enough. And somewhere in those measurements, in the data already collected, or in the data being collected now, or in the data that will be collected in the years ahead, the answer may already be present. Waiting, not hidden. Exactly. Just not yet read. The universe kept its secret for nearly 14 billion years. It can afford to wait a little longer. And so can we. Think about what it means that we are here at all. Not in a grand or overwhelming way, just quietly, gently. The fact that you are lying here, breathing slowly, your body warm and heavy against the bed, that fact is, in a very precise sense, the result of an imperfection. A tiny one, almost undetectable. One extra particle for every billion pairs that were created and then destroyed. That is all it took. At the very beginning, in the first fractions of the first second of everything, the universe was not yet a place of stars or planets or empty space. It was something far simpler and far more violent. A dense, blazing plasma of pure energy, converting itself continuously into matter and antimatter in equal measure. A proton here, an antiproton there, a particle and its mirror twin, born together, existing for the briefest moment, and then finding each other again and annihilating. When a particle meets its antimatter counterpart, both vanish completely. They do not break apart or slow down. They simply cease to be particles at all and become light instead. Gamma rays, the most energetic form of light that exists. Brilliant, invisible, carrying away every trace of what the particles once were. This was happening everywhere, all at once, in the first moments of the universe. Creation and destruction, perfectly balanced. Or almost perfectly balanced. Because something was not quite even, for reasons that physics has not yet fully explained. For every billion matter-antimatter pairs that formed and annihilated, there was one extra matter particle left over. Just one. Not two. Not 10. 1 in a billion. A difference so small, it is almost nothing. And yet, that difference is everything. If the balance had been exact, if matter and antimatter had been created in truly equal amounts, the annihilation would have been total. Every particle would have found its twin. Every proton would have met an antiproton. Every electron, a positron. And the universe, after that first fierce burning, would have contained nothing but light. Gamma rays spreading outward through an empty cosmos, with no atoms to form, no gravity to gather them, no time for anything to grow. No stars, no carbon, no one to wonder about any of it. The universe we live in exists because that balance was imperfect, because the laws of physics, in those first moments, did not treat matter and antimatter in exactly the same way. Physicists call this CP violation. CP symmetry is the idea that the laws of nature should look identical if you were to swap every particle for its antiparticle and simultaneously mirror the universe in space. A kind of deep, elegant equivalence between matter and its opposite. For a long time, it seemed like a reasonable assumption. Matter and antimatter appear, in most respects, to be perfect reflections of each other. But in 1964, two physicists, James Cronin and Val Fitch, were studying the decay of particles called kaons, unstable particles, short-lived, unremarkable in most ways. And they found something unexpected. The kaons did not decay in a way that was perfectly symmetric between matter and antimatter. The mirror was not quite exact. It was a small effect, subtle, easy to overlook. But it was real. Cronin and Fitch received the Nobel Prize for it, 16 years later, in 1980, and in the decades since, CP violation has been found in other particles as well. In B mesons, which contain a heavier quark called the bottom quark, measured carefully at experiments in Japan and in the United States, at facilities built specifically to look for these tiny asymmetries. The asymmetry is real, confirmed, measured with precision. And yet, it is not enough. The amount of CP violation that the standard model of particle physics predicts, the best and most complete theory of particles and forces that we have, falls short of what would be needed to explain the matter-antimatter imbalance by an enormous margin. Not a little short, many orders of magnitude short. The gap between what the theory predicts and what the universe actually contains is so large that something else must be responsible. Something not yet in the theory. This is where the search becomes genuinely open, where the question is not just difficult, but, in a precise sense, unanswered. Not because physicists have not looked carefully, but because the answer appears to require physics that has not yet been discovered. One possibility involves neutrinos. Neutrinos are among the lightest particles known to have any mass at all. Ghostly things, passing through ordinary matter almost without interaction. Billions of them are passing through your body right now, and through the bed beneath you, and through the floor, and through the earth itself, without leaving any trace. There are 3 kinds of neutrino, and they can transform into one another as they travel, a process called oscillation. This was confirmed in 1998 by an experiment in Japan called superchemiocond, which observed neutrinos produced by cosmic rays in the atmosphere and found that some of them had changed identity by the time they arrived at the detector. The question now is whether neutrinos and their antimatter counterparts, antineutrinos, oscillate at the same rate or differently. If they oscillate differently, that would be CP violation in the neutrino sector, and that could matter enormously. Because some theories propose that the matter-antimatter asymmetry did not begin with protons and neutrons at all, but with leptons, the family of particles that includes electrons and neutrinos, very early in the universe's history, before being converted into the baryon excess we observe today. In 2020, an experiment called T2K published results suggesting that neutrinos and antineutrinos do indeed oscillate at different rates. It was a hint, not yet a confirmation, but a meaningful one. A quiet signal pointing in a direction that could, if it holds, help explain why we are here. Larger experiments are being built to follow that signal. Hyperchemiocond, in Japan, will hold far more water than its predecessor and detect neutrinos with greater sensitivity. Dune, in the United States, will fire a beam of neutrinos more than 1,300 kilometers through the solid rock of the Earth's crust, from one detector to another, measuring their behavior with a precision not yet achieved. These are patient instruments, built for patient questions. And the question they are asking is, in the end, a simple one. Why is there something rather than nothing? Not as a philosophical abstraction, as a measurement, a number to be read from data, compared against a prediction, refined over years of careful work. The universe, as best we can tell, spans roughly 93 billion light-years across. Every galaxy in that vast reach, every star burning quietly inside those galaxies, every planet cooling in the dark between them, all of it is made of ordinary matter, the same matter that survived that first annihilation. The same 1 in a billion excess, written across everything that exists. The iron at the center of a star, the carbon folded into a living cell, the silicon in a grain of sand resting somewhere on a beach you have never visited. All of it traces back to that almost nothing difference, that imperfection smaller than 1 part in a billion, which is also, in a way, what you are. A survivor of that annihilation, made of the matter that remained when the symmetry was not quite perfect, breathing slowly now, in the quiet dark, on a planet that exists because the universe made one small mistake. Or perhaps not a mistake. Perhaps a feature so subtle and so precise that we have not yet learned to read it clearly. The answer is somewhere. In the data accumulating in detectors deep underground, in the oscillation of particles crossing continents through solid rock, in measurements being made tonight, by instruments that do not sleep, in places built for exactly this kind of patience. And you can rest now. The search will continue without you, steady and unhurried, the way all the best things do. The universe, as far as anyone can tell, should not exist. Not in the way it does. Not with galaxies and dust and the slow turning of planets around quiet stars. Not with any of this. When the universe was very young, younger than a single heartbeat, younger than any unit of time that maps onto ordinary experience, energy was converting itself into matter and antimatter in almost equal measure. For every particle of matter that appeared, an antimatter twin appeared beside it. And when they met, they erased each other completely. Not destroyed in the way a fire destroys wood, leaving ash and heat, erased. Both particles gone, converted entirely into light. This happened everywhere, all at once, across the whole of the early universe. And if it had been perfectly balanced, if matter and antimatter had been created in exactly equal numbers, the erasure would have been total. Every particle meeting its twin, every twin meeting its end, until nothing remained but a vast, featureless sea of light. No atoms, no gravity pulling matter into clumps, no stars condensing out of cooling gas, no planets, no ground beneath anything. Just light, spreading outward through an empty universe forever. That is what the mathematics predicts. If the symmetry had held, but the symmetry did not hold, somewhere in the first moments, the balance tipped by almost nothing. For every billion matter-antimatter pairs, there was one extra particle of matter, one among a billion. The annihilation still happened. It was vast and total, and it swept through the early universe like a tide. A billion particles of matter met a billion particles of antimatter, and both became light. But that one remaining particle, that single survivor out of every billion, had nothing left to annihilate with. And so it persisted. Across the whole of the observable universe, those survivors accumulated. And from them, eventually, came everything. Every proton in every atom in every molecule, every star that has ever burned or will ever burn. All of it descended from that 1 in a billion excess, that almost imperceptible tipping of the scales. The question physicists have been asking for decades is a simple one to state and a very difficult one to answer. Why was the balance imperfect? There is a name for the property that would allow such an imbalance to form. It is called CP violation. CP symmetry is the idea that the laws of physics should look the same if you simultaneously swap every particle for its antiparticle and mirror the geometry of space. If CP symmetry were perfect, matter and antimatter would behave identically in every situation. They would be created at the same rate, decay at the same rate, interact in the same ways. And the universe would have erased itself. CP symmetry is not perfect. This was discovered in 1964. In a particle called a kaon, James Cronin and Val Fitch observed that kaons decay in a way that is not quite mirrored by their antimatter counterparts. The asymmetry was small, but it was real, and it was the first crack in what had seemed like a fundamental law. They received the Nobel Prize for it, 16 years later. Since then, CP violation has been confirmed in other particles. In B mesons, which contain a bottom quark, experiments in Japan and the United States measured the asymmetry with careful precision. The Babar experiment and the Bell experiment both found it, independently in different detectors on different continents. And yet, the CP violation found in kaons and B mesons is real, but it is not nearly enough. The standard model of particle physics, the most precisely tested theory in the history of science, does predict CP violation. But the amount it predicts falls short of what would be needed to explain the observed imbalance by many orders of magnitude. The theory is correct. As far as it goes, it simply does not go far enough. This is where the search has been for some time now. Not in doubt about whether the asymmetry exists. It clearly does. The universe is here, but in search of the mechanism that produced it, the physics that has not yet been written down. One possibility involves neutrinos. Neutrinos are among the lightest massive particles known. They pass through ordinary matter almost without interaction, Billions of them move through your body every second, and none of them leave a trace. They come in three types: electron, muon, and tau. And they can transform from one type into another as they travel, a process called neutrino oscillation. Neutrino oscillation was confirmed in 1998 by the Super Kamiokande experiment in Japan, a vast tank of ultra-pure water buried deep underground, watched over by thousands of light sensors. The confirmation that neutrinos oscillate also confirmed that they have mass, something the original Standard Model had not predicted. If neutrinos violate CP symmetry, if they oscillate differently from antineutrinos, it would open a path toward explaining baryogenesis through a process called leptogenesis. The idea is that very heavy neutrinos in the early universe decayed in a CP-violating way, producing a slight excess of leptons over antileptons. That excess then converted, through other processes, into the baryon asymmetry we observe today. In 2020, the T2K experiment in Japan published results suggesting that neutrinos and antineutrinos do oscillate at different rates. The hint was strong, but not yet definitive. The measurement continues. The Hyper-Kamiokande detector, currently being built in Japan, will be able to measure this with far greater sensitivity. And the DUNE experiment in the United States will send a beam of neutrinos 300 kilometers through the solid rock of the Earth's crust, from a laboratory in Illinois to a detector buried in a former gold mine in South Dakota. Both experiments are designed for exactly this kind of patience. Years of data, accumulating slowly, narrowing the space of what is possible. Meanwhile, at CERN, antihydrogen atoms are being created and studied. A single antiproton, orbited by a single positron, the mirror image of the simplest atom in the universe. These atoms are held in magnetic traps for up to 1,000 seconds, long enough to measure their properties with care. So far, the energy levels of antihydrogen match those of hydrogen to within the precision of current instruments. The symmetry holds, at this scale, to everything we can currently measure. But the search for a difference continues, because if there is a difference, anywhere, at any scale, it would be a thread leading somewhere new. The universe's existence is, in a precise and literal sense, the consequence of an imperfection, a symmetry that was almost, but not quite, exact, 1 part in a billion. That is the margin by which something exists rather than nothing. And no one yet knows why that margin was there. The answer, if it comes, will come slowly, from data gathered over years in detectors that do not sleep, from measurements made in the dark, underground, far from any city. The experiments are running now. The particles are crossing continents. Somewhere in the accumulating numbers, patient and still, the answer may already be present, waiting for someone to read it clearly. The universe made one small asymmetry. And here you are, breathing quietly. Part of the matter that remains.